Today's November 13th. If you go to uahighrise.org, they posted pictures from Mars today, but they can't post these 3I Atlas pictures from October 2nd. So bizarre. How do you respond to that?
Well, we had 45 days since the images were taken, and there are people involved in the high-rise camera that are not government employees. Some of them are, affiliated with the University of Arizona. They definitely had plenty of time.
But Dr. Loeb, do you believe the NASA administrator? Do you believe the NASA administrator? Do you believe what he just said to
me? I have no issue with him. He's basically repeating what people are telling him.
I don't either. I just want the truth.
Right. So I think we will hopefully see something coming out in the coming days, but it just shows you how sluggish is this system of bureaucracy. I don't necessarily think they are trying to do something, on purpose. It may be just bureaucracy taking over science.
I agree. And that seems like a whole lot of bureaucracy. Again, those photos taken October 2nd. It's November 13th. Dr. Avi Loeb, we will have you back. Good to see you again. Thank you.
A rapid and unexpected change in 3I Atlas has just caught astronomers off guard. In the latest sequence of observations, this interstellar object has begun growing its dust tail at an unusually fast pace, its structure shifting more dramatically over the past few weeks than any model predicted. What started as a faint, uneven plume has now accelerated into a sharply defined tail captured in newly released high-resolution images. At nearly the same moment, a separate report began circulating through radio astronomy networks. A brief, unverified pulse detected near 1420 MHz, the hydrogen line frequency routinely monitored in deep space surveys. The detection remains unconfirmed, but its timing, coinciding with Atlas's sudden surge in activity, has prompted heightened scrutiny from researchers. The situation is evolving quickly, and the newest data demands attention. 3I Atlas, the third confirmed interstellar object to enter our solar system, has been under routine monitoring since its discovery. For months, it behaved more or less as expected. Dim, slow-moving, and largely featureless, a cold remnant from another star system drifting inward. But in recent weeks, its activity has escalated in a way that challenges assumptions about how frozen bodies from interstellar space should behave when exposed to sunlight. The first sign of change appeared as a sunward-facing plume, an unusual morphological feature not commonly observed in solar system comets. Instead of developing the classic tail extending away from the sun, Atlas seemed to push material almost directly toward it, forming a stubby, asymmetric structure that puzzled observers. As it moved inward toward the sun, scientists anticipated that 3I Atlas might begin showing early signs of activity, especially if its surface contained volatile ices, light molecules such as carbon monoxide or carbon dioxide that sublimate at relatively low temperatures. But the manner in which the activity is unfolded is what has taken scientists by surprise. Early imaging showed a faint asymmetric plume extending in a sunward direction, an unusual feature that defied expectations for a classic comet tail. Instead of ejecting dust and gas away from the sun, as most comets do under the pressure of solar radiation, 3I Atlas presented a stubby, forward-pointing feature. This sunward plume suggested that material was being released in a specific direction, perhaps from a localized vent or fracture on the surface of the nucleus. The plume persisted for several observation cycles, but did not grow quickly. For a time, it seemed this unusual shape might remain stable, a strange but static characteristic of this interstellar visitor. Then, almost abruptly, the situation changed. New data from large aperture telescopes in the southern hemisphere, particularly from facilities in Chile and South Africa, revealed that the sunward plume had reconfigured into a more familiar cometary tail, one stretching away from the sun in a long, well-defined line. What startled astronomers was not simply the change in shape, but the speed at which the transformation occurred. In a relatively short window, the morphology shifted dramatically, suggesting that substantial quantities of material were being released from the nucleus at once. Dust analysis, derived from photometric modeling and early spectroscopic readings, indicates that the grains being ejected by 3I Atlas are unusually large compared to those of many solar system comets. Rather than the fine, micron-scale particles typically produced by heating water ice, the dust appears to be dominated by grains roughly a tenth of a millimeter in size.
These grains are comparatively heavy and difficult to accelerate. Their presence implies that the gas flow from the nucleus is steady but not explosive, pushing out larger particles at speeds of only a few meters per second. Such slow, deliberate ejection suggests a nucleus with either a dense, cohesive surface or one containing distinct layers of material that respond differently to solar illumination.
Spectroscopic measurements of gas released from 3I Atlas suggest that sublimation began when the object was still more than 3.5 astronomical units from the Sun. At that distance, water ice remains largely frozen. Only hypervolatiles, such as CO or CO2, would sublimate under solar heating. These volatiles are common in extremely cold environments, and their early release indicates that 3I Atlas likely contains substantial reserves of them. This supports the theory that the comet originated in a region analogous to our own Oort cloud or Kuiper belt, but belonging to another star, an icy, distant fringe where temperatures remain extremely low. The early plume and subsequent tail are already scientifically valuable, but the appearance of a potential radio pulse near 1420 MHz has generated additional attention. The hydrogen line frequency is one of the most carefully monitored windows in the radio spectrum. Because neutral hydrogen emits naturally at this frequency, and because it lies in a relative radio-quiet band, astronomers use it to study galactic structure, star-forming regions, and the distribution of gas clouds. It is also notable because the search for extraterrestrial intelligence, or SETI, has long identified it as a strategic frequency where an artificial signal might intentionally be placed, if any were ever transmitted. The reported pulse was brief and recorded by a small number of observers, none of whom have yet released a peer-reviewed analysis. It may have been a technical glitch, terrestrial interference, or an unrelated astronomical phenomenon. The fact that it has not been confirmed underscores how cautiously scientists approach such claims. However, its timing, arriving as 3I Atlas underwent a dramatic increase in natural activity, has motivated several radio observatories to conduct follow-up sweeps. These surveys aim to determine whether any consistent or repeating signal exists in the region of the sky where the object is located. Importantly, no evidence currently suggests that the radio pulse originated from 3I Atlas, but scientifically, unverified signals serve as prompts for closer examination. Radio telescopes, including both interferometric arrays and single-dish facilities, are now evaluating data collected around the same time. Some observatories will continue monitoring 1420 MHz over the coming weeks to determine whether the pulse was a one-time anomaly or part of a repeating pattern. Even a repeated natural radio emission unrelated to intelligent activity would be a valuable discovery, as few comets produce detectable radio signatures outside of molecular emissions. The physical changes occurring within 3I Atlas are far more important for understanding the object's properties and origins. The rapid evolution of the tail allows astronomers to study how the comet interacts with solar radiation, how dust particles respond to changing temperatures, and how jets or fractures shape the overall morphology. In some images, subtle curvature and brightness variations can already be seen along the tail, possibly indicating multiple active regions on the nucleus. As the object continues its inward trajectory, scientists expect more features to emerge: jets, shells, waves, or distinct dust structures that reveal how the interior is responding to thermal stress. Comparisons to previous interstellar visitors highlight just how unique 3I Atlas is. Oumuamua, the first, showed no visible puff of gas or dust. Instead, its brightness fluctuated in ways that implied a strange, elongated shape or a tumbling motion. It experienced small accelerations that could not be explained by jets or tail formation, leading to numerous theories about exotic compositions like nitrogen ice, hydrogen ice, or wafer-thin fractal structures. 2I Borisov, the second interstellar visitor, behaved much like a traditional comet: a bright nucleus, well-formed tail, and regular release of dust and gas. Its chemistry even resembled objects from the outer solar system. 3I Atlas is different from both. Its early plume resembled neither Oumuamua nor Borisov. Its dust grain distribution, large and slow, does not match most solar system comets. And now its sudden acceleration in tail formation is faster than what typical cometary heating models would predict. The combination of these traits makes 3I Atlas one of the most important interstellar objects for scientific study to date. Because 3I Atlas is currently becoming more active, astronomers are racing to gather as much data as possible before it reaches peak brightness and possible fragmentation. Comets often break apart as they approach the Sun, especially if they contain deep pockets of volatile material or internal weaknesses. Should 3I Atlas fragment, each piece would provide a new surface for observation, making it easier to analyze composition but harder to track the original nucleus. Fragmentation events can reveal internal layering, density variations, and thermal stresses that would otherwise remain hidden. Observatories across multiple continents are coordinating efforts to maintain constant coverage. Optical telescopes provide brightness measurements and dust modeling. Infrared telescopes analyze heat distribution across the coma. Spectroscopic instruments identify gas species released from sublimation. Radio telescopes search for emissions from molecules or any anomalous pulses. The combined data set will likely be the most detailed ever collected for an interstellar comet, surpassing even the analysis of 2I Borisov. As more data arrives, scientists will refine their understanding of how 3I Atlas's dust and gas production changes over time. The tail's shape will allow researchers to determine the comet's rotation period and the location of active regions. Studying the structure of the coma, the diffuse clouds surrounding the nucleus, will help determine how gas interacts with solar radiation. Even subtle variations in brightness can reveal whether the nucleus is elongated, irregular, or fractured. The evolution of 3I Atlas is more than an astronomical curiosity. It is an opportunity to study how icy bodies behave in interstellar space. Many theories suggest that comets are frequently ejected from developing planetary systems by gravitational interactions with giant planets. These objects then drift through interstellar space for eons, accumulating impacts from dust, cosmic rays, and micrometeorites. Their surfaces become hardened, chemically altered, and thermally processed. When such an object enters a new star system, the fresh exposure to light and heat can trigger unusual patterns of activity. Studying these transformations offers a snapshot of cosmic history far beyond our own solar system's borders. The scientific community is watching closely as 3I Atlas's activity intensifies. Whether or not the radio pulse proves meaningful, the rapid evolution of the dust tail, the peculiar grain properties, and the early volatile activity all point to a complex, layered structure shaped under conditions no one can yet fully define. Over the coming weeks, as 3I Atlas draws nearer to the Sun, the rate of change may accelerate even further. Jets may appear, tail structures may shift, and unexpected emissions may emerge. Whatever happens next, the ongoing transformation of 3I Atlas represents one of the most important natural experiments in modern astronomy. A small, ancient traveler from another star system is revealing its secrets in real time, reshaping our understanding of interstellar material. Every new observation deepens the mystery and brings us one step closer to seeing the universe through the eyes of an object that was born light years away.